So we're going to pick up with electron configurations. If you haven't watched the previous video, you may want to. So we're going to start here at n equals 3. So at this point, all these electrons here are in their spots. And one of the reasons why I wanted to show that is because you can see how if I was to write 1s2, 2s2, 2p6, starting from the beginning every single time, I'm going to do a lot of writing. So this right here, this represents the electron configuration for neon. Okay, so what that means is that if I just put neon in brackets, that it sort of summarizes the last full row across the periodic table. So I can write neon, and then the next place where an electron goes is right here in the 3s orbital. So neon 3s1 is the same as writing 1s2, 2s2, 2p6, 3s1. This one's just a lot less writing. And see, we can use neon to show that. Now, if I ionize sodium +1, I take away an electron. This one, it's in the highest n value. So that means that it's isoelectronic with just straight up neon. A lot of times I like to show this as 1s2, 2s2, 2p6, just so I can highlight that it's got a full electron shell. Now, if we go across the periodic table, we're going to skip a bunch of elements here. So phosphorus is element 15, which means this is full, and I've got 1, 2, 3 more here in the p's. This would end up being neon, not equals, neon 3s2, 3p3. And now if I went all the way over to argon, these would end up being full. So this would be neon 3s2, 3p6. We would not write something like argon is argon. That doesn't make any real sense and doesn't show what we're trying to show. Moving on down to calcium. Now again, all the way up to here means that I've got the electron configuration of argon. So instead of saying neon and then 3s, I just pick up at the last noble gas that's filled, which in this case is argon. And that would be 2 electrons in, so 4s2. Okay? I'm going to go across the periodic table over to titanium. So that means I add 2 more electrons. Now the next lowest place that I can add an electron to is not these 4 p's, but these 3 d's. So 2 electrons end up going there. So argon, 4s2, 3d2. And the important thing for us to realize is that the d is equal to whatever the s is minus 1. It's an important thing for us to remember. There is some overlap between these orbitals and the subshells as they get closer and closer together. Okay? So if I just follow all the way across, argon, 4s2, 3d10 for my favorite element, zinc, selenide instead of selenium. So an easy way to think about this is selenium. So I'm sorry, I forgot to fill in for zinc here. And now I want to do selenide. So selenium would be like this. Then I get 2 extra electrons, so they go here and here. So 4s2, 3d10, and then all those filled up the 4 p's. So I'm at 4p6. Okay? That of course brings me to another full energy level, which is all the way over to krypton. So now I'm here at strontium. So that would be in brackets krypton, and then the next 2 electrons go here in the 5s. So this would be 5s2. I can go all the way over to palladium, which would be 10, 9, 8. So krypton, 1, 2, 3, 4, 5, 6, 7, 8. 5s2, 4d8. And then if I want to go all the way over to iodine, these end up getting filled. And then my 5 p's are actually not drawn in here. They're higher in energy than the 4 d's. So 1, 2, 3. These are my 5 p's. And iodine would be 1, 2, 3, 4, 5 elements over. And this would be krypton, 5s2, 4d10, 5p5. This is a very, I wouldn't say easy exercise, but it's made easier with the periodic table. So use a periodic table when you're doing this sort of activity. Okay, so that's something we're going to want to pay attention to. Now lastly, there's a few things I want to summarize with this. So s orbitals hold up to 2 electrons, p orbitals hold up to 6 electrons, d orbitals hold up to 10 electrons, f orbitals hold up to 14 electrons. And when we're going through and writing electron configurations, whatever the p number is equal to the s number. So if it's 2s, then it's 2p, 3s, 3p, that sort of thing. D is s minus 1, as we saw, and f's, which we haven't really filled yet, are s minus 2. This will vary a little bit based on periodic tables that you're looking at. So if I'm looking at cerium here, on the periodic table that's given here in Tro, cerium is in the 6th energy level. So the last noble gas that's filled is xenon, 6s2. The next element is element 57, which is in the transition metal block for the Ds. So I would go 5d1. And then cerium is the first one down in the Fs. So that is 2 less than the S's. So 4f1. This is what you would expect to have written. Now, some periodic tables will have lanthanum on the first element there on the lanthanide series, and some will have it up in another spot. You want to pay attention to the periodic table that you're using and see what you expect. But to go all the way to tantalum, which is element 73, it's still xenon, 6s2, 4f14. I'm going to reverse this because I fill this one before I go back up to this one. 5d1, 2, 3. Okay? And practice will make perfect with this, and there'll be some homework that you can see here. Now, there are some other things I want to draw your attention to. One of them is exceptions. So there are some exceptions to how this works. Copper we'd expect to be argon 4s2 3d9. You can go through and do that, but when we observe it, that means it actually behaves like it's this, 4s1 3d10. That's based on its spectroscopic and magnetic properties. Same thing here with silver. So it's observed to be this way. When it's expected to be this way, it's actually observed to behave like this. So I do not hold you responsible for memorizing these. I do want you to understand that they do exist. Your book calls them out. Lastly, with ions, specifically ions that are in the transition metal areas, this is vanadium. When we ionize vanadium, the highest energy electrons are not necessarily the ones that go, it's the highest N. The highest N here is 4, so that means those are the electrons that go. So this would be 4s0 3d3, and the way that's really written is, well, that would be argon 4s0 3d3. So the way this would really be written is argon 3d3. Okay, those are some exceptions you're going to want to pay attention to, and ions especially. These are things that you will see on homework and quizzes and tests. So good luck.